So this is lecture 3.2, and in this lecture we are going to continue our discussion on stability of control systems. So this lecture is about testing for stability. We have already seen the basic definitions of stability, the definition from the natural response of the system, and the BIBO definition of stability, bounded input, bounded output definition. Today we are going to see how to test for stability. We have also seen that if the poles have negative real parts, that is, they lie in the left half plane. If all the poles have negative real part, all of them lie in the left half plane, then the system is stable, right? If even one of the poles is in the right half plane, right? That is to say, it has a positive real part, the system is unstable. And we saw that if the poles are on the j omega axis and have multiplicity 1, then the system is marginally stable according to the first definition, the natural response definition. And if the multiplicity is more than 1, then the system is unstable. According to the BIBO definition of stability, systems with poles on the j omega axis are unstable. Okay, so this means that the question for testing for stability of any system boils down to finding the poles of the closed loop transfer function and deciding whether the poles have positive or negative real parts. So for example, if you are given a function, let us say, where the closed loop transfer function Cs by Rs, please remember that I'm talking again and again about closed loop transfer function because we have also defined an open loop transfer function. Basically, the overall transfer function is the closed loop transfer function, which is the Laplace transform of the output divided by Laplace transform of the input. So suppose Cs by Rs for some system is given by 5 on s plus 2, s plus 3. We'll see the poles by putting the denominator of the transfer function equal to 0. And this equation is called the characteristic equation. The denominator is called the characteristic polynomial. And once you put the characteristic polynomial, you equate it to 0, you get the characteristic equation. And from the characteristic equation, the roots of the characteristic equation are the poles of the system. So you can immediately say that the poles of the system are on the S plane are lying in the negative half, and hence the system is stable. Right? Now it is not always possible to factorize a system like this or have system so easily. In fact, the poles quite visible like this, right? So what is going to be in the test for stability? How are we going to test for stability? We can make certain observations. What is available to us is the characteristic polynomial, right? And we don't have the poles available directly. We'll have to factorize the characteristic polynomial to find the poles. So one thing that we can observe is that in case the poles are in the left half plane, like in this case s plus 2, s plus 3, the characteristic polynomial s square plus 5s plus 6 has positive coefficients, and all degrees of s are present. All degrees of s, that is degree 2 s square, degree 1 s, and degree 0 6 uh, are present. All degrees of s are present. Now, in case just one of the pole becomes, like for example, a positive on the right half plane, so in this case, the characteristic polynomial has roots at s is equal to 2 and minus 3, which means one of the poles is in the right half plane. So what would be the characteristic polynomial? S square minus s minus s minus 6 s plus 3s, yeah, s square minus s minus 6. So you can see that the coefficients are negative. Coefficients are negative, right? And suppose both the poles are there, right, in the right half plane, then you have s square minus 5s plus 6. Again, one of the coefficients of the characteristic polynomial becomes negative. Similarly, for complex conjugate pole, you might see that some of the coefficients are missing. For example, s square plus 1 is equal to 0. This gives you s is equal to plus minus j. So if this is the characteristic polynomial, then the poles are on the j omega axis. It's a marginally stable system. There is the term of s is missing in this. So you have a coefficient, you have the one term of s square and one term of s to the power 0, no term of s to the power 1. Another example could be multiple poles, like if you have two poles at plus minus j, this would be s square plus 1 whole square is equal to 0. If this is the characteristic equation, this gives you s is equal to plus minus j plus minus j. There are 4 poles on the j omega axis, right? Or you can say there are poles of multiplicity 2 on the j omega axis. Now, if you look at the full form of this is s4 plus 1 plus 2s square. This is equal to 0. So s4 plus 2s square plus 1 equal to 0. Again, if you look at this characteristic polynomial, you see that although all the coefficients are present, right? Although all the coefficients are present, sorry, although all the coefficients are positive, all coefficients are positive, or they are of the same sign, are positive. But some coefficients are missing. And this system is unstable, right? We already know this from the definition. In both definitions, this system is unstable. So this takes us to the conclusion that if the coefficients of the characteristic polynomial are of the same sign, and if all coefficients from the if all terms from the highest degree down to the lowest degree are present, there are good chances that the system is stable. But if this condition is violated, then it is certain that the system is unstable. But the problem is that even without violation of this condition, you might get an unstable system. For example, if your characteristic equation is s cube plus s square plus 2s plus 8, you see that all the coefficients are positive and all terms right from s cube down to s to the power 0 are present. But if you factorize this, this is actually s plus 2 into s square minus s plus 4, right? So you see that here you have right half poles because uh, some of the coefficients are positive and some are negative, right? So this is a characteristic equation of an unstable system, although all the coefficients are positive and all the terms are present. So that means we can only draw a conclusion about the system being unstable if this condition is violated. We are not certain about whether the system is stable if this condition is violated. But in case this condition is violated, that is, you see uh, the coefficients of the characteristic polynomial not being of the same sign, all the coefficients not being of the same sign, or you see any coefficient missing, you can conclude that the system is unstable, right? These are actually necessary requirements for stability, but not sufficient, right? So basically, why are we doing this? We are doing this so that we are able to see whether the system is stable or not by just looking at the coefficients of the characteristic polynomial, right? And there is an important test, right? Uh, that helps us do this more easily, and that test is called the Routh-Hurwitz stability criteria. So this test helps us in order to find whether the system is stable or unstable or marginally stable by performing a test on the coefficients of the characteristic polynomial. We have to make a table called the Routh table, and from the Routh table, which is very simple to make, we can find out whether the system is stable or unstable, and we can even know the number of the number of right half poles in the system, right? The basic essence of the Routh stability criteria comes from this fact that we can actually analyze the coefficients of the characteristic polynomial and have some idea of the stability of the system and the location of the poles. So what we do in this is actually, I'll just show you the table from the book. We actually form a table called the Routh table. Suppose you have this equivalent closed loop transfer function for a system, right? So there is a numerator polynomial in which we are not interested because we do the test on the denominator polynomial. We are looking only for the poles of the system. Number one. Number two, we're talking only about the closed loop transfer function when we talk about the stability of the system. So suppose this is the closed loop transfer function of the system with some numerator polynomial ns and a denominator polynomial which is assumed to be of 4 degree for simplification. So this is ns divided by a4s4 plus a3s cube plus a2s square plus a1s plus a0. Okay. So what we do is we write down the highest degree of s that is present in the characteristic equation on the left hand side like this. So we start from s4, s3, s2, s1, s0 down to s0, and then we write down the coefficient for s4 which is a4. So please remember your characteristic polynomial is a4 s4 plus a3 s cube plus a2 s square plus a1 s plus a0 is equal to 0. So write down from starting from s4 to s0 and then take the first coefficient, which is a4, and write down it in front of s4, and then skip one term, move to the next term, which is a2. Write down a2 here, skip one term and move to the next term, which is a0, and then write down a0 here. And the terms that we have skipped, which is a3 and a1, we write down in the next line along with s cube. So this is how we actually initiate forming the Routh table. Now what we have to do is to actually fill the table completely, make the other entries for the table. And how it is done, this row is called the B1 row. So this is just a second, let me see whether it's, yeah, so it's the B1 row. These are the B terms here that we have, B1, B2, say B3, and this will be C1, C2, and C3. We have to find B1, B2, B3, C1, C2, C3. So how, and the last row also, D1, D1, D2, D3. So this P1 is found. This P1 is found by multiplying like this, multiplying A4 with A1, A3 with A2, and then dividing by A3. So B1 would be A4 A1 minus A3 A2, and that is the determinant of this matrix divided by minus A3. Yeah. And so this gives us B1. B2 is formed by multiplying again the same thing, A4 with 0, A3 with A0, and dividing by A3. So B2 would be minus the determinant A4 multiplied with 0, A3 with A0, and dividing by again by A3, right? And since there is no other column present here, this P3 term would be 0 because there is no other column here. So this term is here, it's going to be 0. Now when we look at the next column, which is the next row, which is the C0, we do the same thing here, but for the row above it, right? So let me just wrap this off so that it is easy for us to see how we multiply. Okay. So for the C1, C2, C3 row, we take the two rows above it, and for finding C1, we take these two rows above it. So we take this row and this row, and we just multiply like this again, A3 with B2, B1 with A1, and divide by B1. So our C1 is going to be A3 B2 minus A1 B1 divided by C1 with a minus sign. The determinant just above it divided by the coefficient just above it with a minus sign. And C2 is going to be this term here. C2 is going to be A3 multiplied with 0, B1 again multiplied with 0, divided by 0, which makes it 0, right? So C2 is going to be minus A3 B1 0 0 divided by B1, right? Which makes it 0. Right? So we can put a 0 here. So this is more clearly illustrated in this diagram here, in this overall table. It's a very simple table to make. You can see that we start uh, with the highest degree polynomial, S4, S3, S2, S1 down to S0. Write down the coefficient for the highest degree polynomial here, SA4. Then skip the coefficient. If the coefficient of the S-squared term would have been 0, we would have written 0 here. We wrote A2 because the coefficient is A2. And then skip one term and write down. And similarly, do the same thing for the rest of the terms which we have skipped. Write them down sequentially in the next row. And then the rest of the table we complete, right? So the first term is obtained here by finding the determinant that we have here, just in the two rows above it, dividing it by this term and multiplying it with a minus sign. And for the second term here, which is this one, again we do the same thing. We take the determinant like this and divide it by this term here with a minus sign. And for subsequent rows, we take the determinants that are just above them in the two rows above them. So for this one, for for example, this term here, we'll be taking the two rows above it, which are these two rows, which are these two rows here. These two rows. Right? So I hope this is clear. Once we make the Routh table, then the test becomes very simple. And what we can do is to just check the stability using a very simple criteria, which is the number of sign changes in the first column. So let me give you a small example. Suppose the characteristic polynomial is SQ plus 10S square plus 31S plus 1030, right? So I'll make my Routh table by writing the highest degree here, then down to the lowest degree, and starting with my highest coefficient here, which is 1, skipping 1, 31, then taking the next the ones that we have skipped, which is 10 and 1030, and then in order to find this term here, I'll multiply like this and divide by minus 10. So this term here, B1 is going to be 1030 minus 310 divided by minus 10, right? Which gives me minus 72. And here, since these rest of the entries are assumed to be 0, so I'll get a 0 term here, because 1 into 0 minus 10 into 0 divided by 10 would give me a 0 determinant. Then for this term here, I take the two rows above it. The two rows above it are this one and this one. So in order to find the term here, C1 here, I take this determinant just above it and divide it by this. So this will be 10 into 0 minus 1030 into minus 72 divided by minus 72, right? 10 into 0 minus 1030 into minus 72 divided by minus 72, right? So that gives me minus 1030. Now we look at the number of sign changes in the first column. That is the criteria. So we look at the first column. This is the first column, and the first column is 1, 10, minus 72, and minus 1030. And we look at the number of sign changes in the first column. So this is plus sign, minus sign, minus sign, and there is one sign change, one sign change. So we say that there is one pole in the right half plane. As simple as that. So basically, essentially, from the Routh table, how do you find out the how do you find out the okay? So we made a mistake here. This was 10 into 0 minus 1030 into minus 2 divided by minus 72, and there is an additional minus sign. So this is plus 1030. So there are two sign changes. So two poles in the right half pole plane. So what is the uh, criteria? The criteria is very simple. The Routh-Hurwitz criteria states that the number of the roots of the polynomial that are in the right half plane, that the number of the roots of the polynomial which we are testing, the characteristic polynomial in this case, that are in the right half plane is equal to the number of sign changes in the first column of the Routh table. As simple as that. So find out the characteristic polynomial from the closed loop transfer function, subject it to the Routh-Hurwitz test, make the Routh table, look at the number of sign changes in the first column, and that is the number of roots of the polynomial or number of poles of the system in the right half plane. If there are no sign changes, that means there are no poles in the right half plane and the system is stable. If there is even one sign change, that means there is at least one pole. There is one pole in the right half plane and the system is unstable. Thanks for listening. So in the next lecture, we'll talk about special cases of the Routh-Hurwitz test. Thanks a lot.